Hello, we're CRATER, an undergraduate team from Caltech founded in 2022.
We're proud to showcase our recent developments and prove that we're ready to compete in URC 2025.
Let's dive into our latest iteration of our rover. Introducing Ernie.
The mechanical subteam designed the rover's chassis, suspension, and transmission systems. We implemented a rocker bogie suspension for stable terrain traversal, with a differential bar to enhance stability. To balance durability and speed, we used aluminum linkages, a chassis, and a differential bar, further reducing mass with an isogrid pattern on the rover plates. Our chain and sprocket transmission ensures high torque and speed while positioning motors safely above the wheels. Maxon EC60 brushless motors with a 26:1 planetary gearheads provide 13 Nm output torque per motor. The chassis houses electrical, science, and manipulator systems and has multiple removable plates to allow for easy access of internal systems. Wheelies, inflatable polyurethane wheels improve traction, clearance around obstacles, and skid steer capability. Our electrical system is built around a modular design. We use a board packed with off-the-shelf power converters and motor controllers, all connected in a neat, easily serviceable layout. At the heart of our power distribution is an active balancing BMS, providing real-time cell monitoring and ensuring safe, reliable energy management. We also practice careful grounding and connector placement to mitigate EMI and keep signals clean. We employ a three-tier communication approach: a 1.3 GHz link for high-resolution, low-latency video, a 2.4 GHz Wi-Fi link, which is our primary channel for control commands, and a 900 MHz long-range radio as a backup for extended range when conditions demand it. This setup has proven dependable in rough terrain, helping us maintain consistent control in video feeds.
The rover's 6-staff manipulator can lift up to 5 kilograms, extend to 1.5 meters, and fold into a space of just 0.4 by 0.4 by 0.2 meters. We use a NEMA 34 stepper at the base for precise rotation, and brushless DC motors coupled with non-back drivable gearboxes for the intermediate joints. A lead screw gripper at the end effector ensures secure parallel gripping and can hold objects up to roughly 10 centimeters in diameter. Everything is managed through ROS2 commands to O-drive controllers, allowing precise control with inverse kinematics. We have validated its 5 kilogram payload capacity at full extension with joint-based control, and tested the gripper on various objects, including irregular and delicate items. We will continue to test inverse kinematics-based control of the full 6-staff arm for smoother operations.
For drive control, we use O-drive motor controllers connected via ROS2 control to ensure that our drive wheels have reliable encoders to determine a uniform speed and distance metric. We also use a GPS module to give us GPS feedback during teleoperation. Using an Xbox controller and WebRTC video, we are able to teleoperate the rover as seen here, where we are driving it from a very long-range distance over a 2.4 GHz Wi-Fi link. As for interfacing with the electronics, all of the motor controllers on board the rover are interfaced via CAN bus to a Raspberry Pi 5, which then communicates via network to a ROS2 node run on a Jetson Orin Nano microcontroller. This Jetson Orin Nano has a GPU built into it, which enables high-speed processing, suitable for a future autonomy stack, which will use all of these sensors shown here to autonomously control the robot and navigate from point to point. This is also able to run real-time image processing, which is vital to the operation of the rover. For the science test this year, we focus on rock imaging and stratigraphic profiles via panoramic imaging. We will use the arm to take a video across the profile of the rock that we want to take a panorama of, and then use the scale invariant feature transform to detect key points at different frames of the image. By using these key points, we can match the images together and create a panorama combining all of those still frames, as shown in the image here. This uses iterative SIFT, which will guarantee that the panorama is close to as accurate as possible, but we will also save the images so that we can do post-processing after panoramic creation. For soil testing, we have implemented spectrophotometry to detect concentrations of organic materials within the soil samples. We are also aiming to implement Raman spectrometry for the competition, which will use the Open Raman framework to have an onboard Raman spectrometer to detect signs of kerogen and natural oils in soil samples.
To collect and cache a sample, the rover can drill to depths of up to 15 centimeters and contain it within our custom auger. After drilling, a probe will descend to our sample depth and record soil temperature and humidity. Thanks for watching our team's progress. We can't wait to showcase our rover at URC. We hope to see you at future competitions.